Such a pleasure to be here today. I was telling Michael that I remember, like, from when I was a grad student at Stanford in the late 2000s, one of the early NMDSs must have been held there when I was going on. And I remember thinking it was such a big deal and all those speakers were so amazing. So maybe that was my perspective as a grad student. But so thanks for the invitation. And today I'm going to talk about convex formulations for flexible and interpretable nonlinear modeling. And so I know that the name of this workshop, of course, is massive data. So today I'm going to talk about data that's really not massive at all. It's actually very small by any standards. But I want to talk about an example where we can actually see with our eyeballs what the results are, and also a topic on which we are all domain experts, so that we don't need to take my word for it or the word of my collaborator. I want us to all be able to assess for ourselves whether or not we're happy with the results of a given model. So in particular, the data that I'm going to talk about is a happiness data set. And this consists of country-level data for 109 countries. And for each country, we have a measurement of a happiness index. So this is measured on something called the Cantril scale. And it's just an average across all the people surveyed, a few thousand people per country, how happy they are on a scale of 1 to 10. Okay, and for each of these countries, we also have 12 predictors, which are things like gross national income, percent of people satisfied with their job, percent of people who think that they have freedom of choice, and so on. And so what I want to do is I want to fit a model to predict outcome using these 12 predictors. And in particular, I want a model that's going to be flexible. So straight away I can see that a linear model isn't going to be what I want, because I don't want to assume that there's a conditional mean relationship that's linear between happiness and these predictors. So the next more flexible thing that I can do in statistics is an additive model. I want to predict a response y on the basis of these p features. I'm going to assume that the conditional mean of y given the x's is an additive function of those x's, where these functions f1 through fp are unknown. And of course, the question is how am I going to estimate them? So additive models have been around for a really long time in statistics. And one of the really classical ways to fit a model like this is by assuming that these functions live in some suitable smoothness class. So in particular, I can say that I want my f's not to be too wiggly. For instance, I could say that I want to in some way bound their second derivative. And that basically amounts to fitting an additive model using smoothing splines. So I can do that on this data. And what I'm showing you are the results for two of the features. So the purple curves here represent different FJ hats. On the left-hand side, the feature I'm looking at is life expectancy at birth. On the right-hand side, I'm showing you the number of scientific journal articles published by year, in a given year. So these are FJ hats, and the reason that there's 10 of them on the left and 10 of them on the right is because I sampled from my data 10 times so that we can get a sense actually of the variability associated with these fits. So any one of those purple curves is the fit that you get if you fit the data once, but if you use the bootstrap to sample from the data, you get a whole bunch of curves. So what I can see if I look at the picture on the left is that in some of these samples from the data, there's a clear positive association between life expectancy and happiness, where countries with longer life expectancies tend to have happier people, holding all of the other variables fixed. But in some of the other data, some of the other samples from this data, still on the left-hand figure, there's actually a really strong negative relationship between life expectancy and happiness. And in still others of the data, we can see that there's really even a non-monotone relationship. So on the left-hand side, we don't get a really clear picture of this relationship. It's not easy to interpret this. The results are highly variable. And also, I don't really believe these results. I think in my heart that there's probably a positive association between happiness and life expectancy, conditional on all the other variables, or maybe no relationship, but I certainly don't know what to make of those fits on the left. So on the right, if we look at the FJ hat, where the feature is the number of scientific journal articles published per year, we now actually get a really consistent story across 10 samples from the data. And the story is that there's actually a pretty strong negative relationship between the number of journal articles published and happiness. So I hear a couple chuckles. We all should feel really bad about this if we believe it. But I'm going to go ahead and say that I don't believe these results. I think that there's a lot of variability here. And also, even if I believe them, I don't think that they're super interpretable. Like, for example, on the right-hand side, I see a negative monotone relationship, so that's great. But like at the point at which it's just a simple negative monotone relationship like that, I could have just fit a linear model. So I'm not really getting any kind of value add by not restricting myself to linearity. And furthermore, it's hard for me to describe this fj hat in any kind of meaningful way other than just to say, it's a negative relationship. So I want to know if I can do better than this classical approach using smoothing splines. So I just need to briefly mention that there's been a lot of work in the statistics and machine learning literature in the last few years on additive models. Most of these papers focus on the high dimensional setting, where we have a lot of variables relative to the number of observations. And I'm building on that work. But in particular, the existing work assumes that those additive functions are smooth. So for instance, it might assume that those additive functions are, have some sort of regression spline basis or something. So as I argued on the previous slide, this is going to lead to challenges in interpretation. I want to be able to take a similar approach, but I want my fj hats to be more interpretable. I don't want them just to be arbitrarily smooth functions. Arbitrary smooth functions. I want them to be structured in a specific way that makes it easy to interpret them. So I want to be flexible. I want to be able to accommodate nonlinear relationships. And I want to be interpretable in the sense that I want this to be no harder to interpret than linear regression. So interpretability is in the eye of the beholder. So what is interpretable to me might not be interpretable to you, and vice versa. But to give you intuition here, I want to come up with a fitted model that I can give to a friend who is not a statistician, not a computer scientist, not a data scientist, isn't going to be using some fancy software. I want to be able to give this model to a friend who wants to be able to look with their eyeballs at the fitted model, and number one, assess whether this fitted model makes sense to them. And number two, actually apply this fitted model without too much difficulty, because I want it to be simple enough that there's like a formula that I can write out that's not too hard. All of which are things that I can't do, for instance, if I'm fitting an additive model using smoothing splines. And I should also mention one thing that's not here, which is I want a formulation that I can solve efficiently. I prefer to be able to get the global optimum and things like that. So our proposal is called the Fused Lasso Additive Model, or FLAM. And what we're going to do is we're going to fit this model, y equals an additive sum of the xj's plus a noise term epsilon. But I'm going to require that my fitted functions f1 hat through fp hat be piecewise constant with a small number of adaptively chosen knots. So by a knot, what I mean is a breakpoint in a piecewise constant function. So like if fj hat takes on two values, then it'll have one knot or one breakpoint. And when I say adaptively chosen, what I mean is that I want the data to tell me where those knots are and how many knots there are. I don't want to be telling the data. So it turns out that this problem is a lot easier if we just have one covariate. So for a moment, we can think about the setting where we have a response y on the y-axis here and a single feature x on the x-axis. So the black points are my data. And without loss of generality, I'm just going to assume that the indices for the observations are chosen so that x1 is all the way on the left, x2 comes next, and so on. So that's completely without losing any generality. That's just the way that my observations are ordered, are indexed rather. And so what I want to do is make a prediction at each xi, and I'm going to call the ith prediction theta I hat. So theta I hat is just f hat of xi. But instead of thinking about estimating a whole function f now, I'm just going to think about estimating an n vector theta. And in particular, I want my theta vector to look something like this, where you can see it's piecewise constant. It has two knots here, 2 breakpoints, but again, I want the data to tell me where the breakpoints are and not the other way around. And so a knot occurs if a given element of theta I hat is not equal to theta I plus 1 hat. So we can formulate an optimization problem for which the solution has the properties that I just mentioned. And so what we do is we look for this n vector theta. We minimize a squared error loss plus a penalty term, where lambda is a non-negative tuning parameter. And the penalty is the L1 norm of d theta, where d is a matrix of 1s, negative 1s, and 0s, which is constructed in such a way that the L1 norm of d theta has elements of the form theta I minus theta I plus 1. And the idea is that when we apply this L1 penalty to d theta, many of the elements of theta are going to be exactly identical to their neighbors. The non-zero elements will correspond to knots. So this is actually a really well-known optimization problem. This is the fused lasso. It's been studied really extensively, and there are incredibly fast algorithms to solve this problem with huge values of n based on dynamic programming. So this is what I would do if I had one feature, but I don't have one feature. I have p features. So I'm just going to extend this in a really direct way. Oh, I should just mention that the fused lasso basically works like this. On the left, we have a small value of the tuning parameter. On the right, we have a really large value of the tuning parameter. And you can see that on the left, we're overfitting the data, and we're paying a large price in our penalty, which are the absolute value, or rather the vertical line segments. And on the right, with a larger tuning parameter, the penalty is much smaller. So if I only had one covariate, this is what I would do. But I have p covariates, so I'm just going to extend the fused lasso. Instead of trying to estimate a single n vector theta, I'm going to estimate p n vectors, theta 1 through theta p, as well as an intercept. And I'm going to, basically, I just have an additive model term here, which says that y is equal to an intercept plus a bunch of piecewise constant vectors. And the way that I force these vectors to be piecewise constant is using this penalty term here. And this is just the same fused lasso penalty that we saw in the case of a single covariate, but summed over the covariates. And now if you look at that penalty term, there's an additional term, p sub j, where p sub j is just a permutation matrix that reorders the elements in the jth feature for technical reasons, so that we're going to be successfully penalizing adjacent elements in the theta vector instead of the order of the elements getting mixed up. So this is a really straightforward optimization problem. We can solve for the global optimum using some standard algorithms that I'll mention in a couple of minutes. But in the high-dimensional setting, if I have a lot of features, I may also want to induce sparsity in my fitted model so that some of the features will be zeroed out. And in order to do that, I can introduce an additional penalty term, which is simply a penalty on the L1 or on the L2 norm of the theta vectors. So now alpha is a tuning parameter between 0 and 1, and when alpha is close to 1 and lambda is large, I'm going to be zeroing out some of my theta j hats completely so that the jth feature won't enter my final model. So this is a convex optimization problem. The problem on the bottom of the slide here is what I'm calling FLAM. And if you look at this optimization problem and you think about how to solve it, there's a really natural algorithm, which is blockwise coordinate descent, where I'm just going to iterate through the features, hold all but the jth feature fixed, and update just the jth feature, and so on. So my algorithm looks like this. I initialize and then I iterate. In order to update the jth feature, I hold everything fixed except for theta j, and I just update theta j. So in order to do that, I need to solve an optimization problem that looks like this. But unfortunately, we run into trouble when we get here, because that optimization problem, it's not that it looks hard, but it doesn't necessarily look so easy. So I started out with one optimization problem. I said I was going to solve it using block coordinate descent. And now I have another optimization problem that I need to solve within a for loop. So it seems like I've just exchanged one problem for another problem. But it turns out that the optimization problem that I have to solve within each iteration of block coordinate descent is really easy as a result of a proposition. And this proposition tells me that in order to solve the optimization problem that appears within each iteration of block coordinate descent, I can simply solve a standard fused lasso problem, which is the equation on the bottom of the slide. This is a standard fused lasso problem for which there are super fast solvers available. And then I just multiply the solution to that fused lasso optimization problem by a constant that I can calculate. So as a result, my overall algorithm for block coordinate descent takes a really simple form where I initialize and I iterate. And within each iteration, I solve just a regular fused lasso problem using incredibly fast algorithms. And then I multiply the fused lasso coefficient estimate just by a constant that I can calculate, iterate until convergence, and I'm done. This algorithm is really fast also because I can use active set methods and warm starts in order to speed things up. So we can see how we do in simulations, and I'm simulating data in a super simple setting. I have 100 observations and 100 features, of which 4 of them contain signal, and the other 96 features are noise. So what that means is that F1 hat, F2 hat, F3 hat, and F4 hat, shown here as colored curves, are signal features, and F5 hat through F5 through F100 are 0. And what I've shown on the left here are F1, F2, F3, F4. So this is a situation in which you expect FLAM to do really well, because FLAM is assuming that the true functions are piecewise constant, and indeed they are. We can compare FLAM to SPAM, which is a proposal from the literature 2009, which assumes that the underlying functions can be approximated well using regression splines. And what I'm showing you here are the results on a test set. So the y-axis is test set error rate. The x-axis is degrees of freedom, which you can think of as being a measure of model complexity that's comparable across these different methods. The orange curves correspond to FLAM for different values of the tuning parameters, and the blue curves correspond to SPAM, which is the existing proposal from the literature. And what we see is that for a fixed position on the x-axis, FLAM has substantially lower test error, and what this means is that we do better in terms of predicting y on a test set. So this isn't surprising, right? Because we assumed that the functions were piecewise constant, and that's actually how I simulated the data. But now let's see what happens if I'm wrong about how the data were generated. So now I have the exact same simulation setup, but the true functions are smooth. So F1 through F4 are shown here on the left, and once again, F5 through F100 are 0. And this is the same figure on the right. Again, degrees of freedom, which is a proxy for model complexity, is on the x-axis, and test set mean squared error is on the y-axis. And again, FLAM shown in orange is doing a lot better than SPAM shown in blue. So at first blush, this seems a little bit surprising, because if the true functions are smooth and FLAM is assuming a piecewise constant model, like it should be pretty hard to approximate those functions on the left using piecewise constants, right? But it turns out that FLAM can do this really well, because FLAM is able to adaptively choose not only the number of knots, but also the locations of the knots. So to see this, take a look at the orange function on the left, and we're going to see that one again on the next slide. So the true function is now shown in black on this slide. That's the true FJ that I'm trying to approximate. On the left is the approximation that I get using FLAM over multiple simulated data sets. So there's a bunch of orange curves on the left because I've simulated data a lot of times. Similarly on the right, I have the fitted function FJ hat from SPAM. There's a bunch of functions because I simulated data a bunch of times. And what we can see is that even though each of those FLAM fits is piecewise constant, FLAM is actually doing a really good job of approximating that smooth function in black by adaptively choosing the knots. Whereas SPAM is just inherently non-adaptive. SPAM is fitting a smooth function, but it can't capture the true function, which is smooth in some places and less smooth in others. So really across the board, we see that FLAM is better able to adapt itself to the data. So finally, we can go back to this little example with the happiness data. And once again, we're seeing FJ hats over resampled data sets, where the function, or rather the feature, is life expectancy on the left and number of journal articles published on the right. The additive model using smoothing spline fits is shown in purple. I should mention that additive model using smoothing splines is basically the low-dimensional analog to SPAM, because this is a low-dimensional data example. So a method that uses smooth function fits is shown in purple, and our proposal FLAM is shown in orange. And we see that FLAM tells us a simpler story that's easy to interpret across all of the samples from the data. FLAM is fitting a model that's telling us that basically, if you're in a country with life expectancy lower than around 75, the happiness level in that country is what it is. And if the life expectancy exceeds 75, then life expectancy is higher by around 0.5 units on this Camhill scale. And on the right-hand side, we see very reassuringly that there seems to be no association between publication rates and happiness. So I should also mention that for all of these figures, tuning parameters are chosen by cross-validation for all of the methods. Okay, so I just want to briefly mention the second part of this talk. The second part of this talk has to do with trying to retain the interpretability of FLAM, but without restricting to additivity. And the way that we're going to do this is by fitting a regression model with a block structure. So what I want to do is I want to fit a model that looks like what's shown on the left. I'm just going to be showing you figures in 2 dimensions for the rest of this talk because I want something that I can show you on a slide. So on the left, this is a heat map. The x-axis represents one predictor, the y-axis represents the other predictor, and the color tells you the value of the expectation of y given x1, x2. So we can see that the mean has a block structure. And I want to be able to fit models that allow me to estimate means that look like that. So just to give you intuition for what our method is going to do before we get into equations, suppose that my true generating model is shown on the left. So that's the true mean. And what I do is to sample observations, I just take the true mean and I add noise. So that gives me the observed data shown on the right. That's just a sample from the true mean plus noise. What I'm going to do is I'm going to draw grid points on top of my observations, where these grid points are just spaced uniformly along the quantiles of the data. So like the vertical grids are at the 1/7, 2/7, 3/7, and so on quantiles of one of the features, and similarly for the horizontal grid points. And now I'm going to try to estimate the underlying mean corresponding to the data in such a way that I want the mean to be constant within each cell of the grid. And I also want adjacent rows in the grid to be identical and adjacent columns in the grid to be identical. So what I'm going to get is a fitted model that looks like this, where again I've said that I want each cell of the grid to have a constant mean value, but also I want adjacent rows to be identical, and I want adjacent columns to also have an identical mean. So I can compare my fitted model to the true mean model used to generate the data, and I see that I came pretty close, although my fitted model is paler in color than the true model. And this is something that generally happens when we apply multiple convex penalties, which is that we overshrink the true mean. So we get the structure right, but we underestimate the brightness. So in a little more detail, I'm assuming that y is just some function f of x1 and x2 plus epsilon. And I'm going to assume that f is constant within each bin of a q by q grid. So all that I need to do is estimate a q by q matrix M. And I'm going to summarize f, or rather I'm going to say that y is equal to omega m of x1, x2 plus epsilon, where omega is just an operator that extracts one of the elements of that q by q matrix M corresponding to the value of x1 and x2. So for instance, in the figure on the top right, there's a little observation shown in blue for which x2 is 1/2 and x1 is -1/3, and omega m of that value of x1 and x2 is just going to be m of 2, 3, m sub 2, 3. So I need to estimate the elements of M while encouraging the adjacent rows of M to be identically equal to each other and the adjacent columns of M to be identically equal. I get a convex optimization problem that allows me to do this by applying penalties to the adjacent columns of M and the adjacent rows of M. And the way that I get this really crisp, the name of our method is crisp, the way that I get this very clean grid-like structure is through the use of these penalties on the differences between adjacent rows and the differences between adjacent columns. So in order to solve this convex optimization problem, we apply ADMM, which is a really a natural fit for this method. And just to give you a flavor for how this works in simulation, I simulate data from the mean model shown on the top left. The model that I get if I apply my method CRISP is shown on the top right. I can compare this to what I get if I apply CART, which of course is a natural approach for non-additive modeling on the bottom left, or if I apply thin plate splines, which assumes a smooth function f on the bottom right. And in this case, if the true mean model has a block structure, then we do a little bit better than CART, but it's pretty much in the same ballpark. But the place that we really shine is actually if the mean model does not actually have this block structure, then what we see is that CRISP is able to really well adapt itself to the structure of the data because it can choose essentially how fine of a grid it wants to use, or rather how fine the block structure that it identifies is going to be. So in an example where the true mean model has a smooth structure on the top left, the CRISP fit is shown on the top right, and the CART fit is shown on the bottom left. We can see that in this case, CART actually does very poorly because it's a greedy algorithm which makes a mistake in one of the first couple splits and can't recover. And just to give you a sense of this, we can simulate multiple replicates from the simulation, simulate multiple data sets from the simulation. And I'm now going to click through and show you the results for more and more simulated data sets from the setup. And we can see that as I click through, CRISP is pretty much doing well across the board, but CART is actually doing very poorly. And again, just going backwards, you can see the CART really isn't capturing the mean structure at all. And the reason we're doing well is because it's not just that we're assuming a block structure and getting it right, because here on the top left, the true structure doesn't have these blocks. Rather, it's that we're able to adapt ourselves to the structure of the data, and we're approximating the data using a series of blocks, but in a data adaptive way, where we can really deal with the fact that the true mean model might not have that block structure. So just to close, since I'm out of time, so FLAM, which I mentioned at first, is the fused Lasso additive model. It's flexible because I can adaptively select both covariates and knots, and it's interpretable because I end up with simple piecewise constant fits that I can explain to a non-statistician or a non-computer scientist. And then second, I talked about CRISP. So CRISP allows me to adaptively partition covariate space into a series of small boxes that leads to a fit that's both interpretable, if I'm right, that covariate space can be well approximated by these boxes, but that actually gives me good performance even if I'm wrong. So these are the papers that I was talking about. This is joint work with Ashley Peterson and Noah Simon at University of Washington.